Okay, so what I want to talk about is when almost all sets are difference dominated. So this is another topic which has very low prereqs to start, and a lot of the problems very quickly involve some of the most advanced results we have in analysis and convergence. So you can really bang your head on stuff like this. Okay, so I'll talk a little bit about the history. I'll talk about some of the main results and some of the proofs. This is all work I've done with small students over the years. I'll talk a little bit about some open problems, which is not surprising given that the point is to try to get you to work on some open problems. Okay, so introduction. So we've talked about this last time, a finite set of integers. The sum set is the set of sums. The difference set is the set of differences. If you want to try to sound highfalutin, you can say that this is related to things like Goldbach, twin prime, Fermat's last theorem, because those all involve what happens to sets when you iterate with itself. All right, so a set is difference dominated. Surprise, surprise, there are more differences in A minus A than there are sums in A plus A. It's called sum dominant or more sums than differences if there are more sums, and if the two of them are the same, it's called balanced. So we expect a generic set to be difference dominated. Addition is commutative, subtraction is not, and a generic pair will give you two differences but only one sum. Yes, you will have the diagonals giving you 0 every single time, so they only give you one difference, but most pairs are not diagonal. Most pairs have x and y different. You have on the order of size of A squared over two such pairs versus only size of A pairs where the two are the same. So you expect the difference to dominate. So the natural questions, do there exist some dominated sets? And if yes, how many? So, well, if you write one down, it's very easy to show that here they exist. And so the question is it surprising to find something like this? Well, we have 0 to 14. So when you're looking at a candidate set, without loss of journal, you can always translate it so that 0 is included. And then whatever number you have at the end is going to be the large number, so you have to have that. So here, if I want you to look at all the possible sets, including 0 and 14, then the numbers 1 to 13 would all be either freely have or don't have. So there's 2 to the 13 possibilities. 2 to the 10 is? About 10 to the 3. Right, see, we did this earlier today, right? 2 to the 10 is about 10 cubed. So then if I want 2 to the 13, that's 2 to the 10 to the 1.3. So this is 2 to the, this is 10 to the 3.9, about 10 to the 4. Right? We can crank through all those by brute force computer search. It's not that bad to do something like that. As we start getting higher and higher up, it gets a little bit harder. You're going up to 29. Here's a quick computer random search of going up to 100, and we can find such sets. There are infinite families as well. But the number of possible sets of size n is of size 2 to the n. A lot of these families are much, much smaller. I'm not going to go into too much detail about constructing the families. You can always pause the slides. I'm not as interested in stuff like this anymore. I'm more interested in phase transition and stuff like that. So we'll say x is a random variable with density f of x, so f is non-negative, integrates to 1. The probability is just the integral under the curve from a to b. For this one, no pretty picture of the Gaussian, I'm sorry. The key quantities is the expected value and the variance. We've seen these numerous times so far today. The binomial model with parameter p of n means all the elements are equally likely to be chosen, and the probability I choose each element is p of n. So the simplest case is p of n is equal to 1/2. It turns out in this case, another way of viewing this is all subsets are equally likely. And so for my probability students, do you remember which music group is involved here? The greatest music group of all time, yes, ABBA. Okay? How many of you have never heard an ABBA song? You should listen to ABBA, great group from the 70s. So I have 4 people in ABBA. And I tell you, each person is equally likely to be chosen, and I have a group of 2 people. Does that mean all the groups are equally likely to be chosen? There are 6 groups of 2 people that you could form, 4 choose 2. ABBA was 2 couples that eventually married and then split up. And they were offered, I think, $250 million to get back together and tour. And they said, you know what? We have enough money, and we really, really don't want to see our exes anymore, so we're going to pass on the $250 million to get together and tour. I'd like to be in a situation where I could afford to pass when getting together with certain people. But if you look at this, there are 4 subsets that are available now. The subset of the 2 married and the other 2 married are no longer accessible. Each person is in 2 of the 4 possibilities. Each person is equally likely to be chosen as everyone else. But if I tell you I choose Benny, that does affect my probability of choosing some of the other people. So you've got to be very careful about what the models mean. And so it turns out that the expected number of terms in A plus A is 2n minus 11. The expected number in the difference set is 2n minus 7. 2n minus 7 is greater than 2n minus 11. You expect there to be more difference dominated. But what we're doing here, and this has never really been attacked, is we're not really quantifying how much you win by. So can you give me an example in life where it doesn't matter if you win by 1 or by 1,000,000? Basketball. Right? Winning a squeaker by 1 point or winning by 30 points, it gives you 1 win. If you are doing various elections, winning by 1 vote versus winning by 1,000,000, doesn't matter. So over here, when we're trying to figure out if a set is difference dominated, if a set is sum dominated, it's a binary decision. You win or you lose. There's no amount, oh yeah, you killed it, you were really sum dominated, versus you just squeaked by and made it. And so over here, just because on average you're more likely to have a large number of differences than sums, doesn't mean that maybe sometimes you don't have more sums than differences. You need to control the variance and how spread out things are.
So in general, is the probability parameter, do these problems, are we always just like assigning the same probability to everything from 0 to n?
Yes, and not much work has been done where you have that varying, and that could be something to explore. The first thing I wanted to look at was maybe the probability was decaying with n, and so in some sense you could then put it on the entire set of integers all at once. But you've got to be very careful because you don't want to have maybe an infinite set, or maybe you just truncate it at some point. So you could definitely look at what happens where it's no longer each element is equally likely. You could put in some kind of more interesting distribution and see what that says. But it's going to make things a lot harder because now, and so it's a great question to ask. The question is whether or not it's a tractable question to ask. So we really want to understand the variances. So the big theorem is let's A be chosen from 0 to n according to the binomial model with constant parameter p. So no independence. Then there's a positive percent of sets that are sum dominated. And Martin and O'Brien were able to show it's at least 10 to the minus 7. We now know it's around 10 to the minus 3. And roughly, here's the proof when p is a half. You expect A to have about n over 2 elements with fluctuations of size square root of n. It's our square root cancellation theorem from before. It's nice that we keep seeing the same stuff again and again. So if I give you a number k, how many ways can you write it as a sum of 2 elements? Well, you would need to have, if you look at k, maybe k is 20. I could have 10 plus 10. I could have 11 plus 9. I could have 8 plus 12. I need to have both elements in a pair. And you want to count and see how many ways there are. And the number of ways is equal to n over 4 minus n minus k over 4. So the smaller k is, or the closer k is to n, let me see here. I want to be very careful as to, I might be assuming here that k is at most n over 2. Or n, but. Oh no, I think I'm just doing k up to n, and by symmetry I get the other stuff. Okay. So if k is very small, then n minus k is close to n, and this is basically 0, which makes sense. If I want to write a number like 6, I don't have that many possibilities. I can do 3 plus 3, 2 plus 4, 1 plus 5, 0 plus 6. If my number is very large, I have a lot of possibilities. So the larger k is, the smaller this is. And so essentially anything in the middle is going to be obtained with high probability, and it all comes down to what happens at the fringes. The first few values near 0 and the last few values near n. So notation. So x tilde fn, or f asymptotic to fn, means that you give me any constants epsilon, epsilon 2, there's some really big number n, such that as long as I'm at least that far down, the probability I'm not too close to f of n is very, very small. And so it's always a question of what scale do you want to do your movements. So I expect to be of size f of n, and now I'm moving below by a constant multiple, a small constant multiple of fn. or moving above by a small constant multiple of Fn. And the probability that I've moved that far in either direction is supposed to be negligible in the limit. So that's what it means to be roughly asymptotic. And then you just define S is going to be the cardinality of A plus A, D is A minus A, S complement is how many missing sums we have, D complement is how many missing differences do we have. And the new model is a binomial with parameter P of n. I want the decay P of n to be going to 0, but not 0 so fast that I don't have any elements in my set. If the probability of choosing an element is 1 over n squared, and I have n choices, I expect to have 1 over n elements. Oh, well, that means I expect my set to be empty. I want my set to have a number of elements going to infinity with n. Maybe it's log n over n, so then I would at least have log n elements. And whoops, I want it now to be growing not at a constant rate because modern O'Brien already handled the constant case. And then the conjecture was that as n goes to infinity, A is almost surely difference dominated. The only way you're going to see a positive percent of the time being sum dominated is when you have a fixed constant probability of choosing an element. And so the theorem that Peter Hegarty and I proved was the following. So I love this function. G of x is 2 e to the negative x minus 1 minus x over x. So you're basically throwing away a little bit of the Taylor expansion of e to the minus x. The probability that we choose our element, if it's of size little o of square root of n, it means it's decaying faster than that, then the difference set is basically twice the size of the sum set. If it's exactly at square root of n, or 1 over square root of n, then this is where we have the phase transition, and the cardinality of the difference set in the sum set is this interesting function g at these terms. And so as c goes to 0, d over s goes to 2. As c goes to infinity, it goes to 1. And that corresponds to there being almost as many sums as differences. And then in this range, the number of missing sums is twice the number of missing differences. So there's a restoration of the symmetry you would expect. So the fascinating thing is this critical threshold that at constant over square root of n, something fascinating happens. So the key ingredients is we need a strong concentration result of Kim and Vu from a few years ago. And we need to deal with dependent random variables. So handling dependent random variables is hard. And so I'll show you a little bit about how you do something like this. So the sketch of the proof, let x be one of the quantities you care about. You prove the expected value of x behaves as you expect. And then you prove that x is strongly concentrated about its mean. So think back to what we were doing with the Zeckendorf stuff about how close things were to, in the longest gap with incredibly high probability. Let's say the number of expected differences is here and the number of expected sums is here. This is the average values. Is it possible that we could have a set that has more sums than differences? Of course. But if the variance now is very small, it's going to be extremely unlikely that this would go up enough and this would go down enough that they would cross. That's what's really going on, is we want to show that they're well separated. And that's how things go. So the setup is we only need strong concentration if the decay is very slow. If the decay is fast, you can do it with Chebyshev's theorem. So Chebyshev is possibly my favorite mathematician. And the reason I love Chebyshev so much is I am an atrocious speller. Almost any way you write down Chebyshev's name has been used. I don't think you can write a way that hasn't been used by someone. Now, within reason. If you're using the Roman alphabet, though, I think you're fine. Now, what I'd love to do is have different spellings of Chebyshev's name based on which theorem you want to use. The Chebyshev theorem from number theory is spelled this way. The Chebyshev theorem from probability is spelled this way. The Chebyshev function is spelled this way if it's for number theory, but it's spelled this way if it's for interpolation theory. And that way you could tell exactly which Chebyshev result you mean by how it's spelled.
There's a T in front.
There's a T sometimes, there's F's sometimes, there's V's. Sometimes they have it with an S instead of a C. I mean, if you Google Chebyshev, I think there's 50 different ways to spell it. So let's let P of n be n to the minus delta. And let's say delta is between 1/2 and 1, so it's decaying fast. So xnn will be 1 with probability n to the minus delta and 0 otherwise. So this is going to be 1 if we choose n to be in our set and 0 otherwise. And then the number of elements we have in our set is just going to be the sum of these indicators. And the expected value is going to be n to the 1 minus delta. You would get 1 with probability n to minus delta, and there are n such sums. So the expected size is small. Now we want to calculate the variance. Okay, so now we have, let P1 of n be the following quantity. Let's let O be the number of pairs where m is less than n. If I have a pair, I might as well say without loss of generality, the first one is less than or equal to the second. For them to be exactly the same, it's going to be lower order. That's the diagonal stuff again. We don't have to really worry about it. How many pairs do we have? Well, we know the size of our set. Our set is roughly the size n to the 1 minus delta. So it should be roughly n to the 1 minus delta, choose 2. Well, we know with very high probability, x is between 1/2 the expected value and 3/2 the expected value. And then we can use that to get very high probability that the number of pairs is in this region. We can be extremely crude here because they're going to be very well separated. When the decay is not so sharp, then we have to be far more careful. This is extremely crude to be different by this much. We could do a lot better than this. And the proof is just, the variance is going to be of size n to the 1 minus delta. So the standard deviation is n to the 1 minus delta over 2. So this is many, many, many standard deviations away. So by Chebyshev's theorem, the probability that you're at least k standard deviations away is at most 1 over k squared. Since the number of standard deviations is growing with n, the probability is essentially 0. And so now we just want to calculate what d over s is. How many more differences do we have than sums? So we'll calculate how many differences we have, we'll calculate how many sums we have, and then we will show that the ratio is 2. Well, essentially, one way to do this is to show every pair generates a unique sum, and every pair generates 2 unique differences. Now, this is, of course, bullshit, because if I take a diagonal element, it's going to always generate 0. But that's smaller order, so we can throw those away. Is it possible I could get the same element twice? That I could have 2 different pairs that sum to the same number? Yes. Could I have 2 different pairs that have the same difference? Yes. But for that to happen, my set needs to have many elements. The fewer elements my set has, the harder it's going to be to have this alignment. And so most of the time, pairs will generate unique elements. And so if the pairs generate unique elements, then you're going to win. Then every pair gives you 2 differences, and every pair gives you 1 sum. So that's the rest of the proof, is just going through and showing this. And so now we need to just estimate how often can you have 2 pairs giving the same difference or 2 pairs giving the same sum. So I'm not going to go through all the details, but have mn, m prime, n prime. All of it comes down to finding good notation. Without loss of generality, the first index is always less than the second index. It's possible n could be the same as m prime. I don't have to worry about m being the same as m prime, because then n would have to be the same as n prime, because they're generating the same thing. But maybe the middle one is the same, so I either have 3 free indices or I have 4 free indices. And so I'll let this be my indicator variable. It's 1 if the differences are the same and 0 otherwise, and I can calculate the expected value. And so when you calculate the expected value, it turns out the number of bad pairs is much, much smaller than the number of pairs, so long as delta is at least 1/2. So it's just a calculation you have to do. So now we want to just calculate the variance of y. So long as the variance isn't too big, then we know that y is going to be close to its average value, and the number of repeated pairs, the number of pairs that give the same value, is small enough that we won't have to worry about it. And so I'm not going to go through the details, but this is just now a calculation using variance and covariance and just indicator functions. And when the dust settles, you show that it is strongly enough concentrated that it can't reach up. So I want to talk a little bit about some of the generalizations and then the possible things. So Ka just means we add A to itself K times. Can we find a set A such that Ka plus Ka is greater than Ka minus Ka? What about we want A plus A greater than A minus A and 2A plus A, 2A greater than 2A minus 2A? Or more generally, can we do this for all A, for all K? So yes, yes, and no. We talked about K generational sets last time. You can have it hold maybe 5 times, 10 times, 20 times, any finite number, but it can't hold forever. And so how would we find such a set? I'm not going to go through the different constructions, but it generates some nice pretty pictures. You know, you can hit pause, you can look at things down. It really comes down to controlling the fringe. That what happens is what's going on at the extreme edges control what happens. And with high probability, anything that could happen in the middle, anything that could be realized, is realized. All right, so I'm going to skip all this. Let's see. No, it's just... Okay, no, okay, so it's... Yeah. No, okay. I think these, yes, I think these numbers are the right numbers. At least one person in the audience might recognize one of the numbers on the slide if I chose the numbers correctly. When was the University of Michigan founded? That'd be 1817. So I know that when I was doing this, there was one person who was an undergraduate from Michigan in the group. And so I know some of these numbers come down to when was Ohio State founded, when was Michigan founded, some of them are scores of football games. When you have the opportunity to choose numbers, it's often fun to just put things in that will make you smile. I know one of my papers, the spelling is a function of a Michigan-Ohio State game. And we were trying to figure out, since he was British and I was American, should we spell things like the Americans or should we spell things like the British? And so the deal was if Ohio State won the football game, we would spell like Americans and submit to an American journal. If Michigan won, we would spell like the British and submit to a British journal. And Ohio State came back in the fourth quarter and won, so we did a quick search and replace, and we spelled center now ER, not RE. We spelled behavior, etc., etc., etc. All right, some open problems. So the one I really want to talk about...
if the word here came up, it would be H-E-E-R?
No. They don't do that, do they?
No. I'm saying if you did a find all and replace for RE to ER.
Oh. I was just talking about in the word center. But yes. Actually, this is a good opportunity to talk about just some general tech skill. When you are writing papers in tech, you should have shortcut commands so that if you want to change something, you just have to change it in one place in the code, and then it changes it every place in the paper. So if there's something you're using many, many times, define a shortcut for it. Never use a hard label. Never say lemma, by lemma 16 or by lemma 1.5. Because if you add something or remove something, it can change. You always want to give things a dynamic label and have tech update it. Using hard labels is one of the worst possible crimes you can do, and it will cause you hours of pain depending on how you have adjusted things. So this is the one that I really want to understand this summer. This is looking at uniformly drawn subsets of A, so each element is chosen with probability 1/2, and looking at the probability of missing exactly k summons. And you see it goes up, drops down a bit, then goes up again. I don't have a better picture of it here, so I guess that's in a different talk. But you have that little bit of a divot. And I would love to understand what's going on in other cases. If we no longer choose things with probability 1/2, but we still fix things with a probability. What if we look at A plus A plus A? Or A plus A plus A plus A? Sometimes it's easier to do a power of 2, because you can combine things nicely. I can understand A plus A, so to understand A plus A plus A plus A, I do A plus A, I do A plus A, and then I combine them. Okay, any other questions? All right, let's hit stop.